don't feel like you have to get lost. Feel free to ask questions if you're like, wait, what was that? And I will be very happy to answer. Okay, so with that said, let's get started. So first of all, I'm just kind of going to briefly go over the stuff that I talked about last time. I don't expect you to remember it very well at all, but it'll also function as a good roadmap for what we're about to do. Then we're going to be working in this presentation in Peano arithmetic, and I'm going to go over the symbols, the formal symbols of that language. And then once that's out of the way, we can start talking about getting the Gödel numbering map back, which we talked about in the last presentation. And then we'll get the diagonalization and finally prove incompleteness. So really quick, what we did last time is we defined a mapping G from expressions to numbers so that E sub n is the expression with the Gödel number n. We write mapping goes like this. We then defined a diagonalization, which meant the Gödel number of this expression. And then we had a set A, which was sort of like the inverse, A star, which was sort of the inverse of diagonalization. And finally, from all this, we were able to prove that if this set is expressible, then the language is incomplete. Let's move on. I forgot what I was going to say. So basically what Peano arithmetic is, it's a formal expression, it's a formal way of dealing with arithmetic. So basically if you've ever had the pedantic desire to prove that 1 plus 1 equals 2, you could do that in Peano arithmetic. So our goal is to prove that Peano arithmetic is incomplete, and we're throwing in the exponentiation. So basically that means we're throwing in certain assumptions about exponentiations, most fundamentally the fact that it is expressible in Peano arithmetic. To prove that it's incomplete, that's because at certain steps it makes it much easier to do that. Later, I am going to prove that even if you take away that component, it's still incomplete. But for now, we're just going to deal with this exponentiation as a sort of crutch. Okay, so now let's get into the thick of it. Let's talk about what this language actually looks like. So the symbols we're going to use, there are 13 of these symbols, and that's what they are. I'll talk about what these mean. Most of them basically mean just what you expect, so like 0 is just 0. This prime is the successor function, so when you apply that to any number, it just gives you back that number plus 1. And in this way, we can represent any integer that we would need to. We just need to put this appropriate number of primes onto 0. So using just these first two symbols, we can represent any integer. This smaller sort of prime apostrophe-ish thing, basically it modifies the f to give us our three operations, and it also acts as the subscriptor of our variable so that we can have more than one variable. This just negates the truth value of whatever comes after, so it's a not symbol. This, though it's normally a superset symbol, it basically is just a little implication arrow. It means P implies Q. And this is special and a little complicated, so we'll deal with that later. Everything else is just as you'd expect. So, throughout this endeavor, we have this notion of in defining things inductively. So, for example, for terms, what we do is we say a term either is a numeral or a variable, or it's a number of other terms added, multiplied, or exponentiated together. So basically what you can do is you can start with numerals and variables, as I've done here. So here I just have a single variable, and then I've added another variable onto that, and in this way you can kind of grow up, build up to more and more complicated ideas, more and more complicated terms by using these rules for building terms. Formulas are done similarly. There are certain conditions that describe whether a formula is atomic. And so atomic formulas are what we start with. And then we can make formulas more and more complicated, such as, by example, putting a negation symbol and using an implication symbol. I have a very simple example here because if I tried to say this formula implies this formula implies this formula, it would get out of hand, get pretty big fairly fast. But this is just basically what the sort of inductive formation of formulas would look like. So you'll notice 13. Yeah.
What's an atomic formula?
An atomic formula?
Yeah.
So the atomic formula is the idea that it's sort of, so in the case of terms, we had the sort of, at the atomic level, is things that we just assume that are terms. So numerals and variables. So that's kind of, you can kind of call a numeral or variable, you can kind of call that an atomic term. An atomic formula is a formula of a certain form. So this formula right here is just an atomic formula. Actually, that's not quite true. The plus right there, it's not an atomic formula, never mind. But it's basically something like x equals y, or x is less than or equal to y. It's something very simple, and we can use that to make more complicated formulas, which would mostly just look like strings of implication, because the only real rule that we have for making new formulas that introduces other new formulas into it is simplification.